much for the introduction and the invitation. It's my great honor to have the opportunity to introduce one of our recent works, which is entitled Combinatorial Optimization with Heavy Decoder towards large-scale generalization. Okay, I'm Zheng Kun from Southern University of Science Technology. Here is my QR code. If you are interested in our works, you can scan it. Okay, my today's talk will include the following 5 parts. Firstly, I will introduce some fundamental knowledge on combinatorial optimization, and then I will share some my opinions on the challenges for solving large-scale problems. And then I will introduce the motivation and ideas for developing NCO models with large-scale generalization. And then is our proposed method, REHD, and then I will conduct a conclusion. Firstly, let me introduce the combinatorial optimization problems, the cell problems. The cell problem is a subfield of mathematical problems, mathematical optimization problems. Its variables are often discrete, and the distance is finite, but as its variables are discrete, so it cannot use the differential it is non-differentiable and cannot use the gradient descent-based measure to solve it. And it's also unpaired and cannot be solved in polynomial running times. And however, for that, the cell problems is often encountered in many applications like the logistics, supply management, and production planning, and so on a lot. So it's very important in the real world. So and then in this work, we focus on the routing problems. Here are 2 basic routing problems that's called the traveling salesman problem, TSP, and the capacitated vehicle routing problems, CVRP. And the TSP is to find the shortest route that with all the nodes exit once and return to the original nodes. That is like this. Here is an example. We often call it instance. And the CVRP is different. In CVRP, each vehicle will have a limited carrying capacity. And it aims to find several optimal routes for several vehicles and to meet the customer demand and with a lowest cost. The cost is often the length of the routes. And here is also an example. We also call it an instance. So there are some classical methods. We call it the exact algorithms, like the dynamic programming and branch and bound. These methods have some pros and cons. Like here, they can guarantee to find the optimal solution, and they can be confident that the solution obtained in the best possible solution without any approximate errors. However, they are very time-consuming, and they require a significant amount of memory, especially for large-scale problems. And they cannot be used in the real world because the real world problems are often very large-scale. And in practice, the approximation algorithm are often used, like here the gradient model, evolutionary algorithm, and coordinate optimization method. This kind of method have some advantages, like they are often very efficient than the exact algorithms, and they can handle the large-scale problems and making them suitable for the real-world problems. But they also have some drawbacks, like they cannot provide a guarantee of the optimality, and they also rely on the expert knowledge for problem-specific design to achieve good performance. Like TSP, we may need to have some. We need to develop a special algorithm called the LKH. And for CVRP, we may need to design another algorithm called the HGS. So in the real world, the problem the civil problem may have a lot of variants. Like here, the VRP can have a lot of variants. So the exact method cannot be used because they are too time consuming. The approximate method can be used, but they heavily depend on the expert knowledge. So sometimes they are should be often need a lot of the human cost. So recently, the machine learning method are very popular, and compared to the traditional method, machine learning method can automatically learn the algorithm rules and can without the knowledge the expert knowledge and or the knowledge specific to the problems. So it can get rid of the huge human costs. And then the machine learning method can train once and use it for multiple times. And the machine learning method also can have some potential generalization capability in solving some unseen instances. And the machine learning method can also better use the parallel computing powers of the GPUs. And here is a brief summary of the existing NCO method. It can be the existing NCO method can be divided into the two categories. One is we call it learning to construct method. That is a method mimic to the mimics the heuristic
Is it still working? Seems to be disconnected.
Doing the same way. That is different is it uses a neural network to replace the heuristics. Like here, the learn to RTC method use a neural network to select nice nodes and until the complete solution is found. And the other one, we call it a learning to improve method. That is, we have an initial solution, and then we use a neural network to improve the quality of the solution, and then until the solution improved towards the optimal solution. So we call these two kind of the method R2C or R2I. In this work, we focus on the first one, that is the R2C method, because it's so a better promise in solving large scale problems. And the existing L2C VRP solvers can broadly divided into two categories. One, we call it autoregressive solvers. That is, we have given a TSP with 4 nodes, and it will iteratively solve the problem node by node. We call it kind of the method is the autoregressive solvers. And the other is the non-autoregressive solvers. That is, this kind of method often to use the neural networks to get a heat map, and then sampling or use the MCTS to get several solutions directly. So this kind of method are often can only work for TSP because they need to use a heat map. CVRP are difficult to get the heat map. And the neural there is a very recent paper also indicated that this kind of the non-regressive, autoregressive methods that is, in these methods, the neural network often plays insignificant roles and mainly depend on the post processing strategies like the MCTS. That is, their promise not depends on the neural network, but mainly depends on the search method. So in this work, we focus on the autoregressive method. That is the first one. Okay, let me introduce the model structure. So the mostly used NCO model often adopt the encoder-decoder based structure. That is like this. Here is the encoder and here is the decoder. And the encoder and the decoder often adopt multi-layer transform blocks. And like here, we have the TSP instance with 6 nodes, and then the encoder will convince each node the coordinates into its embeddings. Like here, we have 6 nodes, and here their coordinates, and then we use the encoder to get their node-wise embeddings. Here also 1, 2, 3 to 6, and then we use the decoder to auto-regressively to produce the solution. The decoder will select one node at each decoding step based on the embeddings produced by the encoder, and one by one, and then until the solution, the completed solution is generated, like this. Let me introduce the model training method. Existing NCO method are often trained via the supervised learning or reinforcement learning. The supervised learning, that is need to know the optimal solutions of VRP instance to use as its labels. Like here, they often use the cross interface loss to train the neural network. It's quite normal. And the reinforcement learning training method often don't need the optimal solutions as their labels. The construction process is treated as the macro decision progress, and we often use, here is a basic one that we call it AC arithmetic algorithm. That is the agent interact with the environment and get rewards, and use the reward to calculate the gradients and to train the model. Here are some works on the baseline, how to do the baseline. Some works use a critical network. Some will use some the average of the population solutions. So next up, we'll share some share my opinions on the challenges for solving large-scale problems. Existing NCO models are often trained using small-scale VRP instances, such as the uniformly generated solution instances of 50 or 100 nodes. Like here is an example of the non-TSP instances. They are uniformly generated with 14 nodes, and they can have very good performance on small-scale problems. Like here, a well-known model called POMO. They can get near optimal solutions on TSP 20, that is the TSP problem with 20 nodes, and TSP 50 and the TSP 100 is very close to the optimal solutions. However, they are when they are applied to the large-scale problems, their performance degenerate severely. Like here, when use these models to solve the TSP 500 or TSP 1000, their performance can drop a lot. Like here, the POMO can be, the optimal gap means that the difference between the solution get by the neural network and the real optimal. The real optimal is generated by the Concord, which is a commercial solver. And so we can find that the gap is really large. And because the model are trained using the small scale VRP instances. So one intuitive question is, can we use it? Can we use let's try to find the reasons why the model trained on the small scale VRP instance is cannot generalize well on the large scale problems. The node we can see here is an example. The left one is the small scale instance that is have 100 nodes. It's different. The right one is a TSP instance with 1000 nodes. We can find that the node distribution from between the left one and the right one is quite different. So that is node distribution of the small scale VRPs is significantly different from the large scale ones. So the policy learned using the small scale VRPs may not be suitable for solving large scale VRP instances. So we may have the following questions. Can we directly use the large scale VRP instances to train the NCO models? The answer is no, because training the NCO models on large scale VRP instances can face the following challenges. First, we need if we use the super learning, we need the label, and the labels are the optimal solutions. For the large scale problems, the optimal solutions are very difficult to obtain. And secondly, the error-based model training may face severe sparsity rewards as the training epoch increases. Positive feedback becomes extremely rare, so we cannot get the positive reward. So the training efficiency can be very, very low. And the computation time and memory overhead of the transform-based solvers increase significantly as the number of nodes increases. And just like the machine translation, long sequence prediction is extremely difficult. There may not exist a deep learning model that can directly solve the large-scale VRPs, especially since they are often NPR. So we may there are some problems, some simplification measure. One possible way is to deal with to decompose the large scale problem into several small scale subproblems. Like here, this one is the large scale problem, and we can use some decomposition measures to get several small scale subproblems. And the solvers for the subproblems can be easier to be trained than the large scale one. And the node distributions of the subproblems share some similarity. Like here, here is a subproblem for 4 nodes, and it can be a little bit similar to the subproblem of the large ones. Like here, for 5 nodes, they are a little bit similar. And this is one way to do the decomposition. And the other way is to reduce the search space. Like here, we can TSP instance. They are in general they are fully connected. However, we can do some reduction and get a sparsely connected graph, and then we do some research can be easier. And in the constructive NCO, the corresponding model is called the local policy-based model. Because the constructive NCO or construct the solution node by node, that is step by step. In each construction step, here is the current nodes. The red one is the current nodes. It only considers the neighboring nodes rather than the whole set of nodes. So it can be the space can be significantly reduced, and the solving time can save a lot. And here are some benefits and drawbacks of the problem simplification method. For the benefits is obviously that is they can significantly improve the solving efficiency, that it can quickly to get a solution. However, they also have some drawbacks, like they may change the problem properties, and making the optimal solution of the simplified problem differs from the original problems. And if the reduction ratio very high, and the difference can be very high. So that is the simplified problem cannot be very small, because if it's very small, the shifts in the optimal solution can be very large. And in addition, to adapt to different large scale problems, and the size of the simplified subproblems are often varies. a bit on the smaller ranges. That is the subproblem. Even we can get the a smaller subproblems, but the subproblem can be of equal sizes. They must they often have varying sizes because to be adapted to different scales, so different large scale problems. So here we get is a motivation for developing the NCO model with large scale generations, because as we mentioned previously, the problem simplification like the comparison or local policy can be used in solving the large scale problems and to improve the solving efficiency. However, the simplified subproblems still of different sizes. So we still need the solvers to have a cross scale generation ability, especially the large scale generation ability. So that is, we need to develop the IS model, have a very good large scale generalization ability. And then secondly, it would be better if the NCO model could apply to the simplified problems or subproblems. Thereby, it can take advantage of the problem simplification methods. So here is the motivation, and then we analyze the model structure of the existing method. So we find that the previous NCO model method use only one encoder, use the encoder only once, but use the decoder n-1 times. That is like here, the encoder using only once to map the node-wide features to the node-wide embeddings, and then it is not used anymore. But the decoders used for several times, they need to produce the solution node by node. So the data input to the encoder is the same sizes. Like here, the size is always n, where the data feed in the decoders is usually varying sizes. Like once we produce a node, and the node cannot be selected anymore, and the selection set can be from n-1 to 1. That is, it really reduced the sizes. And if we divided the features learned by the encoder and decoder into the scale dependent and the scale independent, and then the features learned by the encoder might be highly related to the scale, where the feature learned by the decoder should be mostly scale dependent. Like here, we think that because the data encountered by the encoder are of the same size, so we think that the feature learned by it is often the scale dependent feature. However, the decoder often uses data of different sizes, so we think that the feature learned by it is should be the scale or independent feature. So and the previous NCO models employ the heavy encoder and light decoder structure. Like POMO use 6 layer in the decoder and 1 layer in the 6 layer in the encoder and 1 layer in the decoder. Therefore, we think that they tend to learn the features more related to the node size and even overfitting to the node size. That is why they can achieve very good performance on the small scale problems, but poor performance on the large scale problems. Here the result, we can find that the models have a very good performance on the small scale problem like TSP 100 and the TSP 200, but they have very poor generation performance on large scale problem incidences. And remember that we expect that the NCO models should learn more cross-scale features rather than the scale-related features. So a light encoder and heavy decoder structure rather than a heavy decoder and light decoder, heavy encoder and light decoder structure should be adopted. That is, we should use a heavy decoder with like here, in previous POMO, they use the 6-layer encoder and 1-layer in decoder. And if we use the one layer in the encoder and 6-layer in decoder, we can get a better cross-scale generalizing ability, especially the large-scale generalizing ability. So that's our motivation to develop a heavy decoder model structure. Next is our proposed method. Like here, here is the model structure of our proposed method. That is, we use only 1 attention layer in the encoder and a 6 layer in the attention layer. And especially we use a linear projection to on the starting node embedding and a linear projection on the destination node embeddings, and we remove the normalization layer. The normalization in the original the decoder and encoder, we find that it's not useful, and so we remove the normalization. And then the model structure are like this. And the heavy decoders, because we use very heavy decoders, and it can refine and updates the relations among the nodes, and we 6-layer, and makes more informed node selection for various size problem instances. And the node size vary during the construction, so leading to the scale-independent feature learning. And here is how to train the model. After we have determined the model structure, we need to select the model training method. Here we decided, we compared the super learning and the reinforcement learning. Here are the difference between the two training method. We found that the super learning need labels, while the RO don't need labels. But the RO need a lot of the memory use, and the training efficiency is also lower than the super learning, and the super learning is better suitable for the subproblems. So we choose the super learning in this paper, but we also have a discussion on the reinforcement learning. Reinforcement learning can be used in where if the training data have a very small sizes. So here in this paper we use the super learning, and we use the TSP or TSP 100 as the training data. So the labels are not very difficult to get. We can use the Concord very quick to get the labels. Here we also use some data efficient data augmentation method, and we find that the use a very simple data augmentation can significantly improve its training efficiency. And here we introduce for the data augmentation method. Like here, TSP, if we do some rotation for optimal solution with the TSP solution, like here the red one and the blue one, the solutions doesn't change, and they are the same, but we can get a new data. Like here, the symmetry is also the same. If we do a symmetry, we also can get a new data, but the solution is the optimum solution is the same. Also do a shrink and a little bit noisy. And we found that if we do some data augmentation, and the training efficiency can improve. And inspired by the data augmentation, we do a similar one in our model training. That is, we didn't use a complete solution to do the model training. We just a simple partial solution, and use it for the model training. As we discussed before, our model can be used for the subproblems, that is like here the partial solutions. So we randomly select a number from 4 to n, and use that and use it as a subproblem size and to sample the puzzle solutions. Like here, the puzzle solution number is 5, and then we sample one puzzle solution. Like here, the 6, 5, 4, 3, 2. Like here is the puzzle solutions. And for TSP, we also did the similar ways to sample the puzzle solutions. Here, why we select the puzzle solution is to enrich our training data. That is, for each one TSP instance, we can get a lot of puzzle solutions as a training data. That is, we don't need a lot of labels. So, and then for the sample the puzzle solutions, we use the super learning to train the model. We also use the coarse interface loss, and here is the PI is the selected probability of node I, YI is the label, and U is the number of the available nodes. The available nodes means that the nodes that have already been weighted. Like here, the available nodes, if we select a puzzle solution like 6, 5, 4, 3, 1, the 6 will be the starting node, and the node 2 will be the ending node, and these 3 are the available nodes. And so here U is the 3. And now we have a very trained and we use the super learning and random sampling, and we can train a neural servers. And how we can use it? If we can perfectly decompose a TSP, we can directly use the subproblem solvers directly. However, we cannot get the perfect decomposition. So here we use iteration plus the random decomposition. That is, with random when we use the model, we random destroy a part of the solution and then employ the solvers to reconstruct the solution. We call it a reconstruction-based inference. Like here, once we get the model, we will get firstly we will use a method to get an initial solution like here, and then we randomly select a piece of the solution, that is the puzzle. We call it a puzzle solution. Like here, we select these 5 nodes, and then we destroy it. That is, break down the connections, and then we use our models to reconstruct the piece of puzzle solution, and then we merge the puzzle solutions into the solution, and then get a new solution, and we iteratively conduct the following iterations, the following steps, and can improve the solutions iteratively, and that is the steps. With this kind of inference method, we can get us the solutions with the controllable cost. That is, we can decide we can use a number of iterations to decide how we want to improve the solutions. Like here, if we use here the LED greedy means that we only use a greedy selection. Like here, we only use a greedy selection to select one node, the next node, and the next node, and then until the complete solution is achieved. Here we call it LED greedy. And here is the LED RC, means that we conduct the reconstruction with the 15 iterations. And the 100 RC 100 means that we conduct the RC iterations of 100 iterations, like here. And then here are different iterations. We can find that if we use the RC 1000, we can add for TSP 1000. The previous models except the BQ, which is a concurrent work with us. The other ones are which also published on the same year's NURBS, and the others can have a very poor performance on the TSP 100, but our performance can have a optimal gap less than 1% if we conduct more than 300 RC. And for CVRP 1000, the result is inconsistent. That is, here we use the LK3 as the baseline, and because we know that its GS is more good at solving the CVRP, so the optimum gap can be negative. And here OR truth is also a famous conventional solver. And we can find that if we use the greedy LED greedy, we can get a 5% optimal gap. Only use 1.6 minutes. So and the can be significant outperform or exist measured. And if we conduct 100 or RC, and we can get a less optimal gap and even less than 1%. And use a similar time with arcades. So we also test and compare our method with two. One is the famous one is the HOMO, and the other is the conqueror one, the BQ, which use a similar model structure with us. And we can find that on the TSP library instances, we can significantly outperform these two our algorithm, and the same result also achieved on the CVRP library. And the next is the conclusion. In this work, we propose RED model, which adopts the light encoder and heavy decoder. And we also propose to learn to construct the partial solution rather than the complete solution, which can be more efficient. And we also propose a random reconstruction inference method, which can be make the model use for multi types, and can improve the solution with controllable costs. And here are some potential research directions. And the first is the self-labeling strategy. Like here in this work, we use the super learning. As we know that because in this work we use the TSP 100 for training. However, if we want to use a large scale problems, the label are very difficult to get. And one possible way is to use the self-labeling strategy, and to get the labels and then use super learning. And the other direction is to find a more appropriate decomposition strategies. In this work, we use a random decomposition. And the other one is to develop a more quick, light, and accurate some problem solvers. Here we use the transformer-based blocks. Maybe we can develop a more lightweight one. And we may develop some divide and conquer frameworks, may be very useful. Okay, here is our group's GitHub. All the codes and are released via this website. If you are interested, you can scan the QR code or just copy it the web link. Here is also my homepage. And thank you, Prof. May. My presentation is ended.